I wanted to go over some of the examples with you on section 8.1. So first, we're going to take a look at the mean and standard deviation of the sampling distribution of x bar. The first thing to note is that mu sub x bar is equal to mu. That means the mean of the sample means will be equal to the population mean. So there's really no work required. The mean will be the same. What will be different will be the standard deviation. So sigma sub x bar equals sigma, which is the population standard deviation, divided by the square root of n. So notice that the sample size, n, its square root is in the denominator. This means for a larger sample size, your standard deviation will decrease. This is what we've been saying all along, that the larger the sample size you have, the more accuracy you will have, and that's what this here is showing us. So let's try an example. The weights of pennies minted after 1982 are approximately normally distributed with a mean of 2.46 grams and a standard deviation of 0.02 grams. Suppose a random sample of 10 pennies minted after 1982 is obtained. Describe the sampling distribution of x bar. So anytime we're asked to describe a sampling distribution, we're being asked to provide these two values. You have to give both. The mean of the sample means will be equal to the population mean, which is 2.46. That was given. The standard deviation of the sample means will be the population standard deviation divided by the square root of the sample size. So let's go ahead and put that in a calculator. That's about 0.0063. So notice how much smaller the standard deviation becomes once you're considering a sample of size 10. What is the probability that we obtain a sample mean of at least 2.465 grams? So it's asking us to find the probability that x bar is greater than or equal to 2.465. So we're going to use normal CDF to do this. So we need four things to do a normal CDF. We need the lower bound, which was given as 2.465. The upper bound, there isn't one. It will be infinity, which we use 1e99. The mean we wrote above is 2.46, and the standard deviation is 0.0063. So put this in a calculator. Normal CDF 2.465, comma 1e99, comma 2.46, comma 0.0063. Okay, we get approximately 0.2137. What is the probability that the sample mean is between 2.46 and 2.5 grams? So another probability that x is between these two values. So we do a normal CDF again. So the lower bound is 2.46, the upper bound is 2.5. The mean is 2.46, and the standard deviation is 0.0063 for a sample of size 10. So put this in a calculator. Normal CDF 2.46, comma 2.5, comma mean, comma standard deviation. Getting about, if I round it, 0.5. So I put a couple notes here. It may not be surprising that if the random samples are drawn from a normally distributed population, the distribution of the sample means is also normal. What is surprising is the following conclusion. It actually doesn't matter what the population is. The population can have any distribution. As long as your sample size is large, then your distribution of your sample means will be normal. And this is called the central limit theorem. Saying the sample size needs to be large is kind of vague, and we do have a guideline for that. We say that if the distribution of the population is unknown or not normal, then the distribution of the sample mean is approximately normal. If the sample size is greater than or equal to 30. So I put a few pictures up here to illustrate this. This first picture is giving us a population that is a skewed right population. It's household income. This is definitely not a normally distributed population. However, if you take a look at the distribution of the sample means when the sample size is 4, you can see that the shape is already beginning to change a little bit. If you increase the sample size and make it 10, the shape is looking even more symmetric here. And if you take a sample of size 25, we have an approximately normal distribution. Even though the population looked like this, the distribution of sample means looks almost normal. And that's with a sample size of 25. So our rough guideline is if we have a sample size of 30 or more, we can pretty much bank on the distribution of the sample means being normal, no matter what the original population looked like. And that is actually pretty astounding and is the main reason why we trust sample statistics in the first place. So let's do a couple more examples. The quality control manager of a Long John Silver's restaurant wants to analyze the length of time that a car spent at the drive-thru window waiting for an order. It is determined that the mean time spent at the window is 59.3 seconds. So here we have mu. With a standard deviation of 13.1 seconds, here we have sigma. The distribution of time at the window is skewed right. So we know that the population is not normally distributed, it is skewed. So for part A, to obtain probabilities using the normal model, what sample size is required? The answer will be 30 or higher, or 30 or more. If the population was normal, any sample size would be fine. But since the population is known to not be normal, we need a sample size of 30 or more in order to ensure that the distribution of X bar is normal and that we can use things like normal CDF or inverse normal in our calculator. Part B, the quality control manager wishes to use a new delivery system designed to get cars through the drive-thru faster. A random sample of 40 cars, so here we have a sample size, results in a sample mean time spent at the window of 56.8 seconds. Here's a value of X bar. What is the probability of obtaining a sample mean of 58 seconds or less, assuming that the population mean is 59.3 seconds? Do you think the new system is effective? So they're trying a new system. What we want to figure out is getting a sample mean that low using the original system even surprising? Would it be unusual to get one that low? If it would be, then it might be worth changing to the new system. Otherwise, the new system isn't really effective. We might want to just keep the old one the way it is. So we're being asked to find the probability that X bar is less than or equal to 56.8 seconds. So we'll be doing a normal CDF. We have a less than here, so the lower bound is negative 1e99 and the upper bound is 56.8. The mean, which would be mu sub X bar, and the standard deviation, which would be sigma sub X bar, need to be computed for a sample of size 40. The mean will not change. The mean will still be 59.3, which is the population mean. The standard deviation, however, will be the population standard deviation divided by the square root of the sample size. So that always has to be computed for a sample of the given size. So let's put this in a calculator. Normal CDF, negative 1 E99, comma, 56.8, comma, 59.3, comma, 13.1 divided by the square root of 40. So I got approximately 0.1137. So the probability of getting a time that fast using the old system is about 0.1137, not unusual. What this is telling us is that the new delivery system isn't really significantly changing how quickly people get their order. So do I think the new system is effective? Not really. It's not an unusually fast time under the old system, so it might not be worth making the change. Okay. Let's look at part B. Treat the next 50 cars that arrive as a simple random sample. There's a 15% chance that the mean time will be at or below blank seconds. So we are looking at a proportion here. If we draw a picture of our normal curve, they want us to find basically where's the cutoff for the lower 15%. So if we shade it here, the area here would be 0.15. Remember that anytime you're given an area, this is when you use the inverse normal function on your calculator. So we'll go ahead and do that for this example. So the area to the left was 0.15, that was given. The mean is still 59.3. But remember, this is mu sub X bar. We're looking at a sample of size 50. So the standard deviation will change. it will be the population standard deviation, 13.1, divided by the square root of 50. Okay, so let's put that in the calculator. 0.15, comma, 59.3, comma, 13.1 divided by the square root of 50. Okay, so I got about 57.34 seconds. So that means there's a 15% chance that the mean time will be at or below 57.34 seconds for the next 50 cars that arrive. Let's look at another example here. The lengths of goldfish are normally distributed with a mean 3.5 centimeters and a standard deviation 0.6 centimeters. Okay, what is the probability that a randomly selected goldfish is between 3.3 and 3.7 centimeters long? So this is just choosing one goldfish. So here the random variable is x. So we use our regular normal CDF. We've been given lower and upper bounds. The mean was given as 3.5 and the standard deviation as 0.6. Let's put it in the calculator. Second var is number 2, normal CDF, 3.3, comma, 3.7, comma, 3.5, comma, 0.6. Okay, so I'm getting a probability of about 0.2611. Part B. A random sample of 9 goldfish is obtained. What is the probability that the mean of the sample is between 3.3 and 3.7 centimeters? Okay, so this time the random variable is x bar, which means we need to take that into account when we compute our standard deviation. So we still do a normal CDF, but this time our standard deviation will change. So the standard deviation will be the population standard deviation divided by the square root of the sample size. Notice the sample size is small. That's okay because we have been told that the population is normally distributed. So I put this in the calculator. I get about 0.6827. So notice that even though the bounds didn't change, it was still 3.3 to 3.7 for both of these, the probability became much higher. Let's see what happens to that probability if we increase the sample size. A random sample of 16 goldfish is obtained. What is the probability that the mean of the sample is between 3.3 and 3.7 centimeters? This will be virtually identical to the above example, except that the sample size has changed to be a little bit larger. So the bounds are the same. Oops, I wrote 13 for some reason. Okay, 3.3, 3.7. The mean is the same. This time, the standard deviation changes depending on the new sample size 16. So I'll put this in the calculator. So you'll see that this probability is now even higher than the previous two. What effect did increasing the sample size have on the probability? The probability increased a lot. So remember that when it was one goldfish, the probability was 0.2611. When it was the mean of 9 goldfish, it was 0.6827. When it was the mean of 16 goldfish, it was 0.8176. So why did it get higher and higher and higher every time? Remember that as the sample size increases, the standard deviation decreases. So for just the population itself, it might look something like this, the normal distribution, with a standard deviation of sigma. When you take a sample size of any size, it will decrease the standard deviation and make the curve more pushed up in the middle, like this. And the tails will have a lower area, whereas the middle will have a higher area. And that's exactly what happened here. The larger the sample size, the more the sample means tended towards the center or towards the mean of the distribution, which, by the way, is why we trust statistics at all. We know that if the sample size is large enough, that the sample means will kind of cluster around that actual population mean, which is how we know our sample mean is probably a pretty good approximation of the population mean. Let's take a look at the other end of the spectrum. What if we're looking at something in the tails? What is the probability that a randomly selected goldfish has a length greater than 4 centimeters? we're back to just one goldfish. So we're looking at the random variable x being greater than 4. So this will change our normal CDF slightly. The lower bound is 4, the upper bound is 1E99. The mean and standard deviation have not changed. So let's put this into the calculator. Normal CDF 4, 1E99, 3.5, 0.6. That's about 0.2023. So that was just one goldfish. Now let's take a look at the probability that the mean of a sample of size 9 is greater than 4. So this time the random variable is x bar. So the normal CDF is almost exactly the same, except we will be changing the standard deviation to reflect that it is a sample of size 9. Okay, so I'll put this in the calculator. Okay, wow, so it looks like the probability has gone down quite a bit. So when it was just one single goldfish, the probability was 0.023. Now we're looking at the mean of 9 goldfish, and the probability has really decreased down to 0.0062. Let's take that even further. Let's say the sample was size 16. We're going to find the same bounds here, but a different standard deviation. See if it gets even lower. I think it will. So this time the sample was size 16, so I'm changing the standard deviation here again. And it is so small, the calculator has put it in scientific notation. I have about 4.29 E negative 4. That is about 0.0004. So that is a very small probability indeed. So it should say part H here, EFGH. What effect did increasing the sample size have on the probability? Why is it different from above? This time it decreased, and the reason is because we are now in the tails of the distribution, whereas before we were in the center. So this is also a good thing to note, because what this is telling us is if we were using a sample to approximate if we were using a sample mean to approximate the population mean, we would be really unlikely to get something as high as 4, which is good because we know that the sample mean is 3.5. So we certainly wouldn't want to approximate it with a value like 4. 4 isn't really reflective of the actual population. So it's unlikely for that to happen, which is good. It's kind of giving us a reason to trust a statistic